Hello, my name is Misha Shalem and I work at CppCon. We use modern C++ to create a safe real-time version of robotics operating system, ROS2, with a focus on autonomous driving. And today we're going to talk about practical memory pool-based allocators for modern C++. Now, last year, my good friend and a former colleague of mine, Andreas Pasternak, presented a talk called Safe Software for Autonomous Mobility with Modern C++, where he gave an overview of many things we do, and among other things, he talked about memory allocations and many things we do to avoid them, like static strings and static containers and local memory areas, things like this. And one exact quote from this presentation is, memory pools and allocators are only one piece of the solution, which is true. But today we are going to talk about this one piece in more depth. So what's so special about memory allocations in real-time safety critical environment? Well, the solution should be safe and certifiable, and for exact definition of these two terms, I again invite you to check out Andreas's presentation. He defines it pretty well. But what does it mean practically for C++, for me as a C++ developer, as an engineer? What should I do or what shouldn't I do? Now, we asked a third-party safety accessor, and the answer was kind of straightforward. It should comply to Autosar C++ 14 coding guidelines regarding memory allocations. And maybe Autosar C++ 14 coding guidelines are a bit outdated, as the name suggests, but regarding memory allocations, it's still very relevant, I think. So at Autosar, we have like 3 main rules, and 2 of them is basically the same thing put in a little bit different wording. Now, these 5 bullets are important, actually. We should strive for deterministic behavior, avoiding memory fragmentation, avoiding running out of memory, avoiding mismatched allocations or deallocations, and no dependence on non-deterministic calls to kernel. Now, running out of memory and avoiding mismatched allocations or deallocations is not something we can actually provide as a middleware. It's always something user can do. Can run out of memory or can misuse API and get mismatched allocations or deallocations. But other 3 things we can address, and we are going to. Now, another important rule, which is kind of relevant for our presentation, is that we're actually allowed to allocate dynamic memory, but we can do it only in our init stage, in the beginning. And when we go into operational mode, like full working mode, we cannot do it anymore. So we're allowed to pre-allocate, and this is a good thing. Now, memory pool is known as a solution for most of these points. And I'm talking about memory pool with fixed block sizes. Now, it provides constant time deallocations and allocations and deallocations. It avoids memory fragmentation. It's easy to implement, understand, and reason about, which is actually very important in certification process. So a memory pool with fixed bucket sizes looks something like this. We have like these buckets, and the sizes of the buckets are predefined in two aspects. It's the bucket itself is a fixed size, and the things we can put into buckets should be of the same size. So we see here like the bucket of the things which take 8 bytes, and we have place for 3 of them, and 64 byte slots, and we have 4 of them, and so on. So this is a memory pool, a collection of buckets, right? Now, in C++, we have a problem. And this problem starts with actually this need to know the dimension of all buckets in advance. bucket size is actually a combination of block size and block count, right? And a block count is something which depends on runtime, and users usually have some kind of hard-coded limitation. For example, it may depend on input, it may depend on something really not known in compile time. And in embedded systems, there are usually hard-coded limits for many things. But block sizes should be known at compile time, right? We are in a strictly typed language, and we should know how many bytes everything we allocate actually takes. But the problem is that C++ constructs often hide the real sizes of allocations. If you take a look at things like studmap, list, promise, shared PTR, they all accept a user-provided allocator in some form or another as a template argument or constructor argument. But they never use it. They actually never use our allocator directly. So we cannot derive our block sizes from allocator we provide to these constructs. And the reason for that actually is that if you think about it, stud list never allocates the thing we actually asked it to allocate. So if it's stud list of integers, right, it's going to allocate nodes, and node has at least 2 pointers, like next and previous, and the thing itself, maybe int, maybe something else. And it's completely implementation defined and hidden inside the library. So it can vary between different implementations, for example, right? So what it allocates is actually this internal thing, not what we asked it to allocate, right? So, but we have some good news here. And the good news is that even though allocator we give to the thing is not used, a related one is usually used. And when I say related, I mean this famous or infamous rebind construct, which basically instantiates the same template we kind of provide it as a template argument to the list or whatever, and reinstantiates it with another type. So it's still the same allocator type, but it's different instantiation of this template. So what list is going to do is going to rebind our allocator with something called like list node or something like this internal name. But still, this allocate function we defined in our allocator, if it's our custom allocator, is going to be called just for another type. So this u becomes t. So there is still a place where we should know this size, right? Even though it's hidden under this rebind thing and so on. So what we would like to do, we would like to be able to use any code which adopts standard C++ allocator model without modifications, but allocate from a memory pool under the hood instead of going to the heap or whatever. So in order to implement that, we are going to do 3 things. We are going to create a memory pool itself. We are going to create an allocator which allocates from this memory pool. And we are going to define a way to generate bucket definitions with block sizes, right? According to the actual allocations an allocator does, even if it's some hidden type, like in list example. So first of all, memory pool. Now we are going for a minimal implementation, so some error checks are skipped for better readability, and implementation is not thread safe, even though it's easy to convert to a thread safe, and default alignment is assumed. So again, if we want to be more precise with alignment, we can do that. But for this example, default alignment is completely okay. It suffices. So one thing we would still want to do is to be able to define multiple instances of the memory pool. And the reason for that is that safety critical applications usually require separation of memory pools just for safety. And just as example, a pool per thread would allow to avoid locking altogether, even though it's just one way to do it. or multiple pools per thread, or pool per one thing, whatever it is, right? We can compose it in different ways. Now, let's take a look at bucket implementation. Now, our bucket is going to be something like this, and an interesting thing here is with two pointers, right? We have a pointer to data, which is like the memory area itself from which we are going to allocate for our blocks. And we have this ledger, and the ledger is just a bookkeeping mechanism which uses 1 bit per block in order to indicate whether it is in use. So for example, if we allocate block with index 5 inside this data array, we are going to put bit 5 inside the ledger to 1, and if we deallocate this, we're going to put it to 0. Now, block size and block count is two properties of the bucket, and it gets it into in the constructor and assigns to this two variables. And belongs function actually just tells us if the pointer belongs to memory area of this bucket, and this is trivial. I'm not going to show it. It just checks that pointer is in range, right? We're going to take a look at allocate and deallocate in more detail in next slides. And these three private functions are actually helpers. I'm not going to show the implementation, they're rather trivial. First, finds an adjacent contiguous blocks, a number of contiguous blocks we ask it. So if we need like 4 blocks to allocate, and we'll see why we may want it, it just goes over our ledger and tries to find 3 zeros in sequence, and returns as the index of first of them. Yeah, and now set blocks in use and set blocks free just flip this bits. So for example, set blocks in use, we say, okay, starting from block 7, it's going to be in use, like 5 blocks are going to be in use, so it's going to put like 5 ones starting from this index. And set blocks free does exactly the same thing but puts zeros, right? So we are saying block is free now. Now we are going to take a look at the constructor, which is rather trivial, just 2 mallocs, and of course we do some rounding up for ledger size in order to have enough bits for every block, and we zero everything out, and this is basically it, and the destructor is going to free everything. Now if we need some kind of alignment, it's probably going to be here, so instead malloc we are going to use something which can give us a custom alignment, but again not in this presentation. Now the allocate function takes amount of bytes, calculates the amount of blocks it would take to allocate with bytes, and of course it rounds it up, so our blocks are always fixed size. Yeah, so if our block is like 10 bytes and we ask for 12 bytes, it's going to actually allocate 20 because there's 2 blocks, right? And if we don't have enough contiguous adjacent blocks, then we're going to return null PTR. Otherwise, we are setting these blocks in use and returning the pointer to the beginning of the memory area for our user. Now, deallocate is going to do more or less opposite thing. It has a pointer and bytes, so it can calculate both the index and the amount of blocks, so it can just put zeros in the ledger, and basically this is the whole thing the allocate should do, right? So it's rather straightforward. Now, what is memory pool? It's just a collection of buckets actually, and each bucket has 2 properties, right? Block size and block count. It can also have alignment and other things, but in our example, it's only block size and block count. So a collection of these properties per bucket will actually define an instance of the pool. So how would we define it in a way which would be convenient to auto-generate or do things like this? So what would a collection of parameters look like? How would we define more than one pool instance? Well, we'll do something like this. We will define a kind of type trait called bucket descriptors, and ID here is actually ID of the memory pool. So we have like 5 memory pools. We can have 1, 2, 3, 4, 5 like numbers, or we can do something more interesting like compile time hash of strings or something like this, which is more informative, or to avoid collisions in different files or something like this. But we are going with just integers for this presentation. So our default implementation of this descriptors thing is going to hold exactly 0 buckets. So you see the type here is empty tuple, and empty tuple here basically says, okay, this memory pool is not defined. We don't have any buckets for this. So if you instantiate it with any ID, you get like empty memory pool. But what we can do, we can specialize it for certain IDs and actually define memory pools this way. Now, this file is actually pretty easy to auto-generate once we know all the information, right? So this is what we're going for. Now, here we see the implementation, a specialization of bucket descriptors for memory pool 1, which actually holds 3 buckets of 16, 32, and 1K block sizes. And as we said, block count here is kind of hard-coded. We're not going to address it very much. It is something which is application defined mostly. So adding this specialization and recompiling code basically adds a definition of memory pool. Now we need to use it somehow, right? Now we're going to define some boilerplate, and it looks scary, but it's just that. It's boilerplate to save some space on next slides. First of all, we'll define a bucket count trait, which just makes the tuple size calls tuple size. And we'll define pool type, which is just to the array of bucket and bucket count. And we will define 2 traits, get size and get count, which will help us to extract with block size and block count properties from the previous slide. These two. But to do it conveniently, when we give it like an ID of a memory pool and the index of a bucket inside tuple, and we get block size as a value or block count as a value. Now, when we have all these, we can define our pools very easily. We can define this get instance function, which is instantiated with a memory pool ID. And it's just going to define a static local std array. I remind you that pool type is just std array. And it's going to call this get size and get count on every bucket from left to right and instantiate with our array with actual buckets, right? So when we call get instance first time, everything is allocated and created, and we have our memory pool with this ID. Okay. Now, here's an interesting question: how to choose the right bucket? We have like this memory pool with many buckets of different sizes. So a naive thing to do would be just to go through the buckets until we find one big enough, right? For one block. And it may work in some cases. It would look something like this, very simple. We just go through all our buckets, and once we find one which works, just allocate from it. And if it succeeds, just return with PTR. Otherwise, if we never found the bucket which we were able to allocate from, we just throw std_bad_alloc, and that's it. It would work for things like std_map or std_list. And by the way, I use these STL examples because they are very well known for everyone, and not because something special about STL, right? But it's just convenient to talk about. Now, for map or list, it would work because map and list, they allocate usually, at least in most implementations, they allocate only one type of thing, and they always allocate things one by one. So list nodes are always allocated one by one, map nodes are always allocated one by one. But it's not the case in many other cases. Like for example, it would work, as we said, for map, but it wouldn't work for something like an ordered map. And the reason for that is that an ordered map actually allocates two different things in two different manners. First of all, it allocates a hash node itself, which is basically the same pattern of allocation as a map does. So it's a thing itself, which is holds like key and value, but it also allocates pointers to these things. And it does it because, well, confusingly, it also calls bucket. Bucket, yeah, an ordered map is a hash map, and it has this bucket list on every unique key. So when you do rehash or resize, it's going to reallocate with linked lists of things, or at least in most implementations, it's a linked list of things, and it's going to need some pointers, right? So it's almost always going to allocate them in droves, not like one of them. Yeah. So we have two different things to allocate. One of them is allocated in a one manner, and another may be allocated in multiples. And if you think about it, vector does that, and deck does that, and many other things actually allocate not one but many things. And what can happen? Well, since our buckets are based on the type, we are going to have, if we like do the analysis, we're going to have like two buckets here. One for hash node, which I don't know, let's say 64 bytes. I don't know. And we're going to have this pointer type, which is like 8, right? And we're going to have two buckets, like 8 and 64. But it may want to allocate like 10 pointers. So this is 80 bytes. And we don't have a bucket big enough. So it's going to fail, right? So, well, okay, maybe even like could happen even worse case if it has enough. Like we're going to allocate like 2 pointers, and it's at 16 bytes. So it's going to steal a slot from our hash node, which we never planned for, right? And actually, when it steals this slot of 64 bytes, it's a waste, right? Because it's not going to use all 64 bytes, it only needs 16. So we have a problem here. We cannot use like this first fit strategy. Now we could do something clever here. We could, for example, do compile time analysis and actually bind buckets to hashes of type names or something like this. Yeah, but it would take a longer presentation to actually present solution like this. So we're going for something simpler. What we are going to do, and I claim it would work for an ordered map and for cases like this. And by the way, this whole problem, sorry, I'm going a little bit on a tangent here. This whole problem happens because allocation actually deep down happens in bytes. We kind of lose information about how many things we are going to allocate or what type we are going to allocate. And the interface of bucket is defined like this because it kind of mimics how PMR memory resource defined, which does exactly the same thing. It just gets size. We don't know if it's size for one thing or for 5 things, or what the original type was. So we lose this information. So we need to do something with size only. Well, it's not necessarily the case. As I said, we could do a more sophisticated solution which actually takes into account the type name itself in some way or another. But again, it's not in the scope of this presentation. So what we are going to do is something simpler. Yeah, we're just going to calculate the minimum amount of wasted memory and minimum amount of wasted blocks, and the bucket which gives us that is going to be good enough. And again, my claim is it's going to work for things like an ordered map. Now, in order to do that, we will define a helper structure. And index here is just an index of the bucket. Block count is how many blocks an allocation would take, and the waste, how many bytes would be wasted if we allocate from this bucket. Doesn't matter from one block or multiple blocks. So how more bytes the bucket would actually provide in integral like blocks than the allocation actually needs, right? And we want minimum waste. we want minimum waste, but if the waste is the same, we are going for less blocks. So if we do that, and operator less here is basically a sort predicate here, right? We can sort with infrastructure and find like minimum waste and minimum block count. So here's the code. I'm not going to go through it line by line, but the idea is pretty clear. We just take the allocation size, required allocation size, and we're going through all our buckets and we calculate this infrastructure for every one of them. There are two cases, like when we can allocate from one block or when we need multiple blocks, but in the end we have this waste and block count calculated for every bucket. And when we are going to sort, and by the way, stud sort here is not used because stud sort, at least by definition, allowed to allocate, and we can't allocate here, so it's a kind of implementation of sort which for sure does not allocate. By the way, I don't think stud sort will allocate in this case, but in most implementations I know, but still it's allowed to in the standard, so it's kind of custom sort. Let's say it's quick sort and log n something. Okay, and when we do that, we have this deltas list from least waste and least block count to the worst, like to most waste and most block count, and we're trying to allocate in this order. And I'm saying that if you're creating something like this for an ordered map, it's going to work. It's going to work properly. It doesn't matter from which bucket it allocates in the end, we will have enough memory for everything, right? So again, it's not the best solution, it's just a simple enough solution to put into this presentation. The best one would be to map types directly to the buckets by hashing their type names or something like this. But again, that would work as one of the solutions, okay? Now, we introduced a problem here, by the way. We kind of introduced fragmentation back, because we are able to allocate more than one block, and as we said, many of the containers may allocate more than one thing at a time. We may use multiple blocks, and that means we are going to create these holes in our ledger, which kind of local fragmentation inside the bucket. Now, theoretically, this is a problem, but practically, if users keep memory pools separated and understand allocation patterns and understand what limitations working with like embedded solutions actually imply, it's not that of a problem, because if you think about it, like an ordered map in embedded application is going to be probably of fixed size, because anyways you have a limitation on max amount of things you can put into it. So the best thing would be to do like rehash or resize in the beginning to the constant size, and you will never go beyond this size, because anyway you have a limited amount of slots for the thing itself. And well, it's not going to manifest. So the problem is not going to manifest because you never deallocate with pointers and so on. But of course, it requires an understanding of the mechanism behind the constructs you use, how they allocate, how they deallocate. And yeah, it does not. We don't have a like 100% solution for fragmentation, but at least it's very local and should be very well understood when and why it can happen in this case. And again, for some cases, you may go with a simpler solution like first fit and one block only. As I said, it will work in many cases, but not all of them, right? So deallocate. Well, deallocate is very simple. It just goes through our buckets until it finds the one the pointer actually belongs to, and it deallocates. That's it. It's just that simple. So, well, two functions we still need to define for our like allocator usage. Is this isDefine function, which basically just does bucket count on the pool ID we provide. And I mean, we defined a default implementation of our bucket descriptors is actually tuple of 0. So if it goes for default implementation, that basically means that the memory pool is not defined, right? And this is important actually. This function is const expert. We will see why it's an important optimization opportunity for the allocator actually. And now initialize function here is just a helper which calls get instance, which creates this static local variable, and we probably want to call this initialize before we go operational for every pool ID, and it just returns the result of is defined. Now we are going to create an allocator, and our allocator should implement standard C++ allocator model compatible with stud allocator traits, and it should be bound. We want it to be bound to a specific memory pool instance and compile time. And the reason we want that is that many constructs can kinda silently migrate things from one allocator to another. And if allocator is convertible, we can, when we move things between containers, we can inadvertently move them between memory pools, and we don't want that. We want our allocators be specific for memory pools and not be convertible to, and maybe the same kind of allocator but bound to another memory pool. We want it compiled time protected. Now, we also want our allocator to transparently allocate from another resource until memory pool is defined. So until we run our analysis and we can know the bucket sizes, we want everything still kind of working, and we want developers not thinking too much about where it allocates from. So by default, we want our allocator to be able to allocate from probably heap or something before we go into full certifiable mode. And we have buckets defined. Now, and of course, we also want our allocator to be able to help us to define these buckets, because we said that it knows all the information we actually need. So we should be able to extract it from it. Now, let's take a look at usage scenarios just to get some taste of how it may work. So we have this static pool allocator, which has two template arguments here. And the second one is actually the memory pool ID, right? So in this example, we have list of integers and vector of such lists, and they both are located from the same memory pool, which is not recommended, but you can do that, right? You can just say, okay, I have one memory pool with different bucket sizes, one for lists of ints and another for kind of ints or list not ints or whatever, and we will just use the same allocator, and it's going to be properly propagated and so on into vector. Yeah, when we create like vector member, it's going to be propagated into list, and everything is going to be allocated from the same memory pool. Now, another way to do that would be to use stud scoped allocator adapter and define separate memory pools. And when we do that, it's just like stud scope allocator adapter normal usage, right? But we create two different static pool allocator types, as you see. Because we take different integers, it's different types, and we will see they cannot be converted to one another. So we are kind of protected from migrating, right? So we need scoped allocator adapter here in order to actually keep things separate. Right. Now, I'm going to skip all the boilerplate code, and the reason is it's completely identical to something like stud PMR polymorphic allocator. So you can take a look at how this all construct functions implemented and propagation work, and all this support in allocator traits and different types of constructors is actually implemented in the polymorphic allocator. But we're going to take a look at the parts which are relevant for us, right? And this is like the most relevant part, except allocation itself. And the interesting thing is that rebind here actually rebinds only for allocator which bound to the same memory pool ID. So you can rebind to like any memory pool, just the same one. And same goes for copy constructor and assignment operator. So it's always it's always protecting itself from skipping memory pools. Now, another interesting thing here is this upstream resource, and this is like PMR memory resource, which by default initialized with get default resource, which is usually new delete resource, which basically means that if this ID pool is not defined, we are able to go to upstream resource and allocate from that, which gives us an opportunity in the development stage to work with like normal heap, for example, right? And of course, we have a static bool initialize memory pool function, which is a helper which forwards to our corresponding memory pool initialize. Okay, now if we take a look at allocate, it actually makes use of this const expr is defined function, and it checks if our memory pool is defined. Oh, okay, we are in like certification mode. So we're going to allocate from our memory pool. And if it's not defined, we're going to allocate from upstream resource, which probably is going to just do new or something in the end, right? And otherwise we just don't have, we have neither of this, and we just throw. And of course we can put something like static assert, but if you compile with like certifiable defined or something that only first option is viable and so on, we can do things here. And by the way, T here, I just reminder, T here is the actual type we are going to allocate for. So if it's like some internal list node or something, it's going to be known here at this line, right? So we're going to use this information. Now, how to collect the type sizes? Of course, we could just put something like stdc out and print here the size and so on. But it wouldn't be ideal. And the reason it wouldn't be ideal is because, first of all, we kind of need 100% line coverage, because some allocations may happen rarely or under some circumstances and so on. But it's doable. We can get this coverage. Maybe it's maybe unpractical, it may be impossible even in some applications, but maybe we can do that. So why wouldn't we just print out these sizes? Well, we won't have information about call site. We won't know, okay, we'll see here the allocation of X bytes, but we don't know why it's here. We don't know the call graph, how it came here, who actually invoked this allocation up the call graph, right? And it would limit us. We wouldn't see many interesting things about what actually and where allocates in our program. And it also kind of harder to prove that we cover all allocations. Again, if you have like 100% line coverage, it may be the case, but anyway, it's hard to prove when you do it in runtime. So what we want to do is to register all calls to allocate in the compiled code. So we want to just take our compiled code, and regardless of the runtime flow, which functions called, which functions maybe never called, we still want to proofably be able to know all the allocation properties, sizes, and maybe alignments and so on. And of course, it would be very nice to see the call paths which led to these allocations for like debug and simply analysis purposes, right? So what we are going to do, we're going to inject some instrumentation, and our instrumentation is going to look like this. Just a dummy call to a function here. It's called type_rec, and it has these three template arguments, which is ID of our memory pool, the name of the type, size of the type, and in real code it's going to be probably a line of the type. Now, this dummy function is actually a dummy function. It doesn't do anything. What we want it to be is just a call which we can actually extract from our compiled code and see that this is a call that happens, and these are these template arguments which we can use to generate our bucket definitions. So The allocation is trivial. Again, it's the same thing. If memory pool is defined, we're going to deallocate from the memory pool. Otherwise, we're going to deallocate probably from heap or another memory resource. And the third case should not ever happen. Now we only need a way to generate bucket definitions according to the actual allocations, right? So in order to do that, we are going to compile the code with Clang into LLVM bitcode because it's so easy to analyze and so easy to work with. We will implement a custom LLVM path or multiple passes which would be able to compose the list of all unique allocations per pool instance. We want this information like for every pool instance. And we would want to see the call graph for every allocation for, again, debug and kind of general insight purposes. And we would want to automatically, if it's possible, generate buckets and memory pool definitions. So we will run our path with on our bitcode with LLVM opt2. And LLVM opt2 is just a utility from LLVM suite which can run a custom path. They call it optimization path, but in this case it's analysis path on a bitcode file. Now, a bit of technical details here. We would want to compile these debug symbols in order to see this information in our call graph, where things were called from, and so on. We probably would want to prevent optimizing out our instrumentation calls, and maybe there are better ways to do that, but -0 will do the trick. It just prevents optimizer to throw away our empty calls to typerec. And we would want to use emit LLVM to compile into the bitcode instead of the native instructions. And we probably want and debug defined to get the release version of data structures if there is any difference, but it's okay. It's of course up to you. You may want to do it with debug versions for some reason. Okay, now after that we can now one bitcode file is basically equal to one opt file. So when we compile into bitcode, we have this one like result of compilation of one CPP file in a BC file, bitcode file. Well, we may want to link them together into the whole program or big chunk of a program in order to run this optimization path on all of them together. So LLVM link does exactly that. It just takes a bunch of BC files and produces one BC file which all these files are linked together in. Now, this is actually a minimalistic path. It doesn't generate anything, but it does print out the all unique allocations with pool ID, size, and type. And this is actually the whole code you need for this. It's just the whole project you need for this, and this is impressive. I think it's a function path, something which in LLVM terms called function path, and this is called this because it's called on every function in the module you analyze. And what it's going to do is just going to check if a function we call now, the mangled name of this function is typerec. It's going to extract all this information we put there, like pool ID, size, type name, and print it out, and that's it. We have all these things. Of course, we don't have call graph here. We do not generate. Header files, but again, I think it's impressive that you can put it on one slide and pretty big font, I would say. Now, the real thing, I'm not going to show, it's just too much of a code, but the real thing is going to be not function path, but module path, because we want call graph, so we want information from the whole module. And we're going to run a depth first search at DFS, starting from entry points, which is usually main or test main, some kind of function you actually start running with. And every time we discover a type reg call, we're going to register allocation type, and we're going to print the call graph for this allocation. And we're going to check for recursions along the way, and we're going to drop these branches because such branch cannot end in allocation. It's just something else entirely. Now, finally, the list of all unique allocations, we can translate it into a header file with specialization or with bucket descriptors. So let's take a look at an example. Main calls F calls X defines this list, which allocates, creates a list with static pool allocator on memory pool with ID 3. Yeah. So when we run our real pass, we're going to see something like this. We're going to see a call graph for pool ID 3, size 24, and real type we see here. The name of the type is internal think of list node. And we see the call graph. So if we go from bottom to top, we see that, okay, main is skipped here, but in the real output, it would be main here. But main calls F calls X, and then pushback calls, which calls allocate node, and so on and so on. And we come to our allocate function in the end. And of course, we have all debug information here, file and line, so we can get a good insight what happens here and why it allocates the way it allocates. Right? Now, we have some caveats with the call graph though. And we cannot actually build a call graph, or it might be incomplete, because of virtual calls or calls for a function pointer or inline assembler with some well-known limitations, right? Because some of them depend on runtime, and inline assembler has a different kind of difficulty. Now, what we can do in order to mitigate this, we can combine both approaches. So we can still build this call graph for convenient and nice information, and then we can complete it with functions which are kind of orphaned in our program, which not in the call graph yet, but they're still in our code. So we can just combine the first approach I showed and the second, right? And we will be probably sure that we cover everything if we do that, right? We may cover too much, right? We can go to some unreachable function and so on, but it doesn't matter. The important thing, we cover everything, right? If you have unreachable code, it's something to deal with anyway. It's not exactly our problem. Now, when we do all that, we can run our opt, and it's going to look something like this. It's a bit scary command line, but basically what it says is run opt and load our custom alloc analyzer path and generate our header called mydevs HPP, starting from entry point main, and this is regular expression. You can put everything here. And program BC is our compiled bitcode file, and we ignore output of the opt. Now, what is going to generate for our example on the previous slides? It's going to be something like this. It's going to generate bucket, and it's going to generate bucket descriptors. And in our case, we had only one stud list, so it's going to be block size 24, and it was memory pool ID 3, so this is what we're going to have. But of course, more buckets can be here, and more specializations for other memory pools can also be here. Now, when we do that, we just include this file, recompile, and hopefully all our allocations now go to our memory pool instead of memory resource, meaning instead of the heap. So ideally we are done. We just need to figure out block counts and things like this, but other than that, we just seamlessly switch from allocating from heap to allocating from our memory pool here. And just to recap, yeah, it's we all know that memory allocations is a fundamental part of C++, and they have to be deterministic for safety critical applications. And memory pools is a good solution, but it's kind of hard to use with C++ allocator model. And instrumentic allocator combined with an analyzing tool can be a certifiable solution for this problem. It's just one of the possible solutions, and it can be improved immensely in many regards, but just an idea how you can do things. And thank you very much for your attention. Thank you. That's all I have for today. And if you have time for questions, I would be happy to answer them. Thank you. Hi. Hello. Can you hear me, guys? Carlos, can you give me thumbs up? Cool. So I'm going to address questions. And the most popular one by far is, why do I use malloc in the bucket instead of new? And yeah, I knew that at CppCon you cannot show a bucket with malloc, it's a sin. But the reason is purely historical. It can be, of course, it can be new. The reason is with original code in C++ 14, not in 17, and it uses alignment allocation. So we don't have aligned alloc or new with alignment in C++ 14, and that was POSIX mem align, which I changed to malloc like on the slide. But yeah, it can be new, so nothing particularly interesting about it. Now, are there any changes, gotchas, details that change when we need a pool of physically contiguous memory, say from kernel space driver allocation? Okay, I'm not an expert on Linux kernel, but I think, just general knowledge, as far as I know, it would be something like kmalloc or something, kzalloc, something like this on kernel level, and we would need to map it through driver or prod file system, something like this. But I'm not really an expert. We have guys who really work on kernel more, and I'm not one of them. But yeah, it would come instead of malloc. Yeah, something like memory map to something allocated in the driver, I guess. Now, what is LLVM bitcode? Yeah, this is a huge problem. I haven't said that, right? And yeah, I mean, that's a problem with the presentation. I should have said that. LLVM bitcode is an intermediate representation which Clang and general LLVM toolsuit uses for compilation. So it's a little bit like Java virtual Java bytecode or Microsoft's intermediate representation like C# and all of the family of languages are compiled into. So the bitcode is like virtual assembler, it's like high-level assembler. But the thing with the bitcode is that it's file compiled into this intermediate format are easy to manipulate, easy to analyze, easy to just traverse functions and the whole module. It's basically we don't have reflections, right? So it's like the closest thing to compile time reflection which we can get. It's not exactly C++, it's like this virtual assembler, but you can go and, for example, check out all function calls or what arguments they take, and so on and so on. So you can just learn a lot about your program. So basically, LLVM uses this for optimization passes, like whole optimization passes work on this virtual assembler, and then comes process which called lowering. This is like compilation into native code and additional optimizations on the native code. So again, bitcode is an intermediate representation in the LLVM compiler suite. Now, can a memory pool be able to grow dynamically, add more buckets as needed, or it's only pre-allocated to a fixed size up front? Of course, you can make it grow dynamically, but it kind of defies the purpose, right? Because if it grows dynamically, you're probably asking for memory from operating system, and this is going to give you like this non-deterministic behavior, which we're kind of trying to avoid. But one thing we could do, and this question kind of makes sense in one other regard, you don't have to do everything static. You can do things like more dynamically in initialization stage. Like when all classes are setting up, they can add buckets for things we are going to use. And when you're going into your running stage, when you're actually operational, and you don't add any more. So you can do things more dynamic, and we indeed do things more dynamic. Just the reason I haven't shown that is that it's a relatively small talk, and I needed to show the whole idea, like the whole chain of what you do with like compile time analyze. Now, okay, I don't understand what the injected instrumentation is doing for us. Well, it actually doesn't do anything. It's just there. Like the whole reason for this dummy function is to be called. It's like what we need is the name with template arguments, which all we need actually encoded into this name. So when we analyze like compiled program tree, we can just go and see where this function is called. And for us, it's like just a marker that this function is going to be called from every allocation. So if we kind of went and collected all these instrumentation calls, we for sure, like 100% sure, we covered all the allocations in our compiled code. In your implementation of memory pool, can we throw exception during initialization too? Yes, during initialization is probably the best time to throw exception. You probably is going to terminate or switch to like a parallel pipeline or something. So if you want to crash, it's probably the best time to crash in the beginning and not in your operational mode. Okay. Would the test PMR test allocator together with stack trace proposal be an option to collect type sizes? Well, it has exactly the same problem as printing to STDC out. You kind of need to be sure that every possible runtime scenario is covered, and this is something which is kind of hard to prove. I mean, with sufficient line coverage, you can prove that, but it can be impractical in some cases. The advantage of doing it on the compiled code, like analyzing compiled code, is actually that it's provable, even if your code is unreachable, even if it's called like 1 in a million years or something, and you don't have tests for that, you still can be sure that if you analyze compiled code, you're going to cover it. But if you do things in runtime, it's not sure. It's not something you can certifiably prove, let's say. Okay, is the full source code available anywhere where we could take a further look? Well, not yet. We are talking. It's kind of intertwined with our proprietary code, and we're still talking what we would like to kind of open source or so. I don't have the code, unfortunately, but maybe I will at some point. No promises though. How do you handle exceptions for this critical system? That's a great question, actually. Well, it's a hard problem, and we're still working on it. We have many ideas, but generally speaking, there is no magic here. Like in most cases, you probably want to use exceptions only for really critical scenarios, and you want to terminate immediately. So you don't use exceptions. You use exceptions in order to calls to terminate and die. Yeah, in most cases you probably want something like boost outcome or stood expected, something like this, I think. Do you have to analyze these graphs every time you update your compile? Unfortunately, yes, but it's just a general idea how you can do things. And one thing we do, we don't use it actually as it is that much. We use it, for example, for creating like more generic type traits. Yeah, you can think about writing special kind of test which being analyzed will allow you to generate like type traits which are actually more flexible, and you can use them as a part of your code just to do more like compile time, like real compile time, not in generated code, but in real compile time to actually access your sizes. Yeah, I would be available. I think I will. Yeah, no problem. I will be in hallway for next like 10 minutes, 15 minutes if you want to talk to me, and can be more if there is interest. Okay, so are there any issues with allocation of memory in physical address space? Malloc on allocated virtual address space and each page on allocated physical. Yeah, of course, it's a kind of toy example. If you really want, like, this is like the first question which I actually answered, kind of answered. I don't know a good like really deep answer for this, but of course you need something more like not malloc, but something more like real-time allocation. You kind of need to write a driver or do something with kernel in order to make sure your memory is contiguous and actually physically contiguous. Yes, so malloc isn't a real example. Yeah, I think this one is also kind of answered. So thank you very much. I'm going to be in the hallway for the next like 10 minutes. If you want to talk to me, please come. Thank you very much for your attention. Thanks. Bye.